vector v with given magnitude in the same direction as u. And so they give us 2 bits of information. The magnitude of v is 15, and u is the vector 1, 2. So this kind of builds off of what we just talked about with Mitch from our homework assignment number 41, where we had to find the unit vector. So, you know, I talked about the unit vector. Unit vector is the vector with magnitude 1, and we can calculate the unit vectors, but we didn't really do anything with the unit vectors yesterday. So now, how can we apply the unit vector to a problem involving other vectors? First, I think about it like this. So let's think about it visually, kind of like 26 and 29 from the homework. Let's get an idea of what's happening in this picture. We have a vector u that is the vector 1, 2. Okay, so there's vector u. Does vector u have the desired magnitude that we want for vector v, which is 15? No, definitely not. If we calculate the magnitude for vector u, we would do the square root of 1 squared plus 2 squared. Think about the right triangle that's formed right there, which is the square root of 5. Okay, so that is not the magnitude that we want. Okay. So we come up with this issue and we're like, well, how are we going to change it so that we're on that vector, we're going in that same direction as the vector u, but we have a distance of 15. And so what we're going to do is we're going to now use the unit vector. So I have vector u. I'm going to scale it back so that I get a unit vector. Okay, so the unit vector would have a length of 1. And it would be on the same vector as u, so in the same direction there. So we're going to calculate the unit vector. Think about what we did with Mitch. We're just going to take our vector 1, 2, and we are going to divide by the magnitude, which we know now is the square root of 5. So calculate your unit vector. And if you're okay with this, I'm going to divide and rationalize at the same time. So 1 divided by the square root of 5 will be square root of 5 over 5. And 2 divided by the square root of 5 will be 2 square root of 5 over 5. If you want to write that extra step, you can. 1 divided by square root of 5, 2 divided by square root of 5. So that's my unit vector. And what do we know about that unit vector right there? It has a magnitude of 1. So it has a magnitude of 1. It's going in the same direction of u. How can I now change my unit vector so that it has the magnitude of 15 that I want for vector v? Multiply by a scalar. Okay, so to get this magnitude of v, okay, we're going to multiply by the scalar. V is 15 times the unit vector. If I have 15 unit vectors stacked on top of each other, they'll add up to 15, and I'll have that magnitude that I want. Okay. So over here, we're going to multiply by the scalar, if you want to make a note. And we've already practiced scalar multiplication with vectors, so you just have to distribute it to both the horizontal and the vertical component. When I do that, the 15 divided by 5 is going to reduce to 3, so I'm going to come up with a new vector v that is 3 square root 5, and then it will be 3 times 2 square root 5, so 6 square root 5. If I calculate magnitude for that vector v down there, and I do like the square root of 3 square root 5 squared plus 6 square root 5 squared, I should get 15 in the end. And if I calculate like slope, think about what Lily was saying, like rise over run, vertical over horizontal. 6 square root 5 over 3 square root 5. The square root 5s are going to cancel. It's going to be 6 over 3, which is 2 over 1. That's the same slope as u, 2 over 1. So they're going in the same direction. Any questions about that? That's one use for a unit vector. Okay, so pretty handy. Okay, now we're going to talk about, and this is what the majority of our class today is going to be about, and it's going to be a big part of tomorrow when you do some word problems. So we're going to get magnitude and the direction angle. It's going to be given to us. So I have drawn those on this picture here of the coordinate plane of vector v in quadrant 1. And I've labeled, I know the direction angle theta, I know the magnitude of v. My question is, given those two bits of information, can you write any vector in component form? So remember, component form is like v sub 1, v sub 2, where our initial point is at 0, 0, the origin.
Yeah.
Yes. What are you going to use, Mason? Trigonometry. Okay, so immediately in that picture, can you sort of imagine the right triangle that we've seen multiple times yesterday already? Yeah? Okay, just drop down your terminal. Drop down from the terminal point to the x-axis, create that right angle, and then we have a right triangle right here. Now, we will need some kind of placeholder for the horizontal and the vertical component here. So remember yesterday when we did direction angle, instead of using like v sub 1 and v sub 2, I said, let me just call that point AB. So I'm going to call my terminal point AB over here, which that then allows me to label the sides of that triangle. So I know my horizontal component is A and my vertical component is B. And then Mason said, use trigonometry. So what kind of trig stuff can you write here? Someone besides Mason, tell me something triggy I could write. Triggy is next.
Sine b over the magnitude. Or theta. Sine of theta is equal to b over the magnitude.
Do you agree with that trig statement? The sine of theta is equal to b divided by the magnitude of b? Good, thank you, Ethan. What's the other one we could write? Cosine of theta is equal to a divided by the magnitude. And then remember, our job is, we don't know a and b. Okay, because if we knew a and b, then we'd have component form, so we won't have this issue. We don't know a and b, so they can't be part of what we need to write it in component form. So let's solve for a and b. What would you have to do to both equations in order to get a or b all by itself? Multiply by what you're dividing by, the magnitude of v. So if I multiply both sides, it's weird, times the magnitude of v, then I'll have expressions for the vertical component is really the magnitude of v times the sine of theta, and the horizontal component a is really the magnitude of v times the cosine of theta. So can you write any vector in component form given just the magnitude and the direction angle? Sure. Looks like this. Magnitude of v times cosine theta, comma, magnitude of v times sine theta. Very important, okay, that we're okay with this. So I'm going to put a little star by it. Very, very important. If given the direction angle and the magnitude, you could write it in component form, Could you also write it in linear combination form? Remember, linear combination is the one where you're adding the two terms with the standard unit vectors I and j. So then these pieces here become the coefficients to I and j. So we also would be able to write it in linear combination form. I'll say most of the time I work in component form, unless my directions are asking about linear combination. But make sure you're okay with linear combination, because sometimes you have to like work backwards from that. I think that might be a given piece of information. So linear combination would be magnitude of v cosine theta times I plus magnitude of v times sine theta times j. I would just like everybody to notice that I cured Jennifer for a hiccup.
That was really impressive, Austin. I don't think they'd ever go away.
It was your full commitment to the process that helped your cure happen. Okay, let's put this to use in an example. Find the component form, please. Given that the magnitude of v is 5 and theta is 30 degrees. And while you get started on this, I'll also say, as you're working, if you recognize the angle is from the unit circle, then avoid using your calculator and get exact values from the unit circle. So we will use our calculator sometimes, but if the angle is from the unit circle, choose those values that you know for cosine sine from the unit circle. Use the stuff we just wrote down. You know magnitude, you know direction angle. Plug them in. This would be my setup. 5 times cosine 30, comma, 5 times sine 30. Anybody got my cosine of 30 degrees from the unit circle? I heard from Lily already today. Anybody else know your cosine? Not mentioned. They're always giving me the answers. Dylan?
Would be radical 3 over 2.
Yep, square root 3 over 2. What's my sine? 1/2. Okay, and so then I could write it 5 square root 3 over 2, comma, 5 halves. Okay, so I have component form. Cool. That's it. Now, on the next example, it's going to work a little bit differently. I think there is more than one way to answer the next question. So I'm going to put it up. I'm going to give you about 30 seconds to like copy it down and just like think about it and kind of look back at the stuff that we've done so far today. And then after 30 seconds is up, I'm going to ask you to kind of like share out with the people around you. What would you do to get started? Because this one is a little bit different. Okay, so this is our next example. The magnitude of v is 2. And we want to make sure that the vector v is going in the direction of negative 2i plus 3j. Can you write that in component form? Okay, have a quick discussion with the people around you. What do you think you could do? And there could be more than one way to do this. So what do you think is an option to get started?
Yeah, more dimensions.
Oh,
That's the magnitude. Sorry, I was kidding. Yeah, that would work.
Okay, let's come together. You'll have a volunteer to share what some of the groups said. What would be some options to get our component form?
Kind of solve how we did find the original, the magnitude for component or regular negative 2, 3. And that'd be radical 13. And then you would just divide that out like we did and then rationalize it.
Okay, so you're talking about our unit vector method where maybe we would write it in component form, negative 2, 3, divided by square root 13, which gets you negative 2 square root 13 over 13 and 3 square root 13 over 13. Okay, so that's your unit vector. Is that your answer then?
Now you multiply by 2.
Oh, okay, and then multiply by the scalar. Okay. So when I multiply by 2, then I would come up with negative 4 square root 13 over 13 and 6 square root 13 over 13. Okay. Is that the only method that groups talked about? Mason, your group talked about something different?
You could take the inverse tangent of negative 2/3, and then you get an angle.
Okay, so the theta is equal to the inverse tangent of 3 over negative 2, which, did you guys get an angle for that? Anybody? I think it's negative 56.13.
Yeah, 0.3.
Oh, 0.31. Okay. 0.31, so you can find the angle, and then remember that angle is because we're doing arctangent in the calculator. Consider it with where V is actually located. Since it's negative 2I plus 3J, it should be in quadrant 2. So we would add 180 to that. Our real direction angle is 123.69.
Yeah.
Okay. So just in terms of practicing direction angle there, your real direction angle is that angle, 123.69, to get you into quadrant 2. And then you could do component form like we did for part A. Okay. So you could set it up and do 2 times cosine 123.69 and 2 times sine of 123.69. And then you get decimals. I'm thinking negative 1 point. Can anybody get me my decimals?
Negative 1.11.
1, 1. What comes after 1, 1?
Well, it's negative 1.01939.
Okay, so negative 1.109. I'm gonna round out. I'm only gonna round out to the thousands because, like, I now have all those decimals. Like, I just think round to hundredth or the thousands. I'm just doing the thousands. Okay, and then what's the other one? Negative or positive?
1.664.
1.664. Okay. So if you wanted to, you should be able to do the work that Lily kind of gave us. If you type in negative 4 square root 13, make sure you close your parentheses if one opens, and then divide by 13, you should get negative 1.109, all that other stuff. And same for 6 square root 13 over 13, you should get the 1.664. So the nice thing about the stuff in blue is you get an exact answer versus in green you have that rounded answer, but either one is acceptable. So you could take your pick on your homework which way you're going to approach it. Do you want to use the unit vector or do you want to use the component form that we just talked about? Either one is fine. Any questions on those? Okay, here's another example where we want to find the component form for the sum of u and v with the direction angles theta u and theta v. Okay. So that theta sub u and theta sub v is just a way for us to keep track of like which angle belongs to which vector. Okay, so it's just a way to name the angles. When I read my directions, I want to make sure I know, like, what am I actually going to try to do? My answer should be a component form. So I want a horizontal component and a vertical component. And it's the component form for the sum of u and v. So that means I'm going to need to add u and v together. In order to be able to add vectors, I need their component forms, so that I could add horizontal components and add vertical components. Remember from our discussions yesterday, the sum of two vectors is also called the resultant. So you could also see that in a set of directions. If it said, find the component form for the resultant, that resultant would tell you add the vectors together. So spend a little bit of time at your desk and see if you could get the component form for the sum of vectors u and v, which means you're going to have to find vector u and vector v so that you could add them together. So see if you could do that. I'll give you a minute or so to kind of work that out. So I would.
And since those angles are on the circle, we should get in like brackets and
Excellent work. As I'm walking around, I instantly saw people setting up the component form given the magnitude and the direction angle, which is what I would do. Remember that if the angle shows up on the unit circle, we should give exact values. So we know that the cosine of 45 degrees is square root 2 over 2, and the sine of 45 degrees is square root 2 over 2. So we should use the exact value there. We will get 2 times square root 2 over 2, which would be square root 2, and then square root 2 for both the vertical and the horizontal component. And then we can do cosine of 90 is really 0, and sine of 90 is really 1. So then multiply those, and v is 0.5, yes?
Yeah.
And we want the component form of the sum, so the last step you have to do is add those together. Okay. So u plus v is equal to, you would do negative or square root 2 plus 0, which is just square root 2, and then square root 2 plus 5. If you're giving an exact value, that really is as good as it gets. Square root 2 and 5 are not like terms, so you can't add them together, leave them alone. Now, if you type that into your calculator, you'll get a decimal, and that is okay, but I would encourage you, like when you're doing your take-home quiz, I prefer, if it's an angle on the unit circle, that you leave it in its exact form. The last two examples, I believe that we have are word problems. So our first problem is a water balloon. Exciting. We've got a water balloon with initial velocity of 40 meters per second. It is being launched at an angle of 60 degrees above the horizontal. And we would like to find the vertical and the horizontal components of the velocity. First thing I would do in most of these is draw a little picture, a little diagram. So I'm going to draw a water balloon. And I'm going to look at it from the horizontal. I know that it's going to be launched at an angle of 60 degrees above that. Yes, Ethan?
Because of gravity, wouldn't it need to be a parabola?
Well, that would be its actual path. Yes, but we're not really looking at that. So we just want to, what we're looking at is like its initial velocity is 40 meters per second, and we want to get horizontal and vertical components of that initial velocity. So think about that like the initial velocity is going to be our magnitude for our vector, and then we're going to get the horizontal and vertical components of that. And we'll be using that tomorrow in a word problem where we calculate work that is being completed.
Okay.
So it's not necessary to think about like a parabola here. Okay. So I would label my 60 degrees, and then like I said, I got 40 meters per second. And you want to get the horizontal and vertical components of velocity. So that's trying to find these two pieces right here. Okay. We have our component form for that. Okay. So think about component form. We would do 40 times cosine 60 and 40 times sine of 60. And that would give us both the horizontal and the vertical component. So 40 times square root 3 over 2. And 40, nope, I got that right. I got that switched around. 40 times 1/2, thank you. And 40 times square root 3 over 2. And then simplify that to be 20 and 20 square root 3. So I could say more specifically, if I wanted to, that my horizontal component is 20 meters per second and my vertical component is 20 square root 3 meters per second. The fact that you can distinguish between horizontal and vertical is going to be important tomorrow, again, in those work problems. Some of you who have done physics, you already know what is the formula for work.
Space and time.
Maybe we don't know.
I'm thinking non.
Force times distance. Yep. Okay, force times distance. So we will also have a conversation in the video tomorrow about how you don't use all parts of the force. You only use the part that's moving it in the direction that you want to go. So that's in the video tomorrow. So you'll need to pick. Do you want the horizontal or do you want the vertical?
Wouldn't that water balloon be traveling at something close to 90 miles an hour though?
It's a really fast water balloon. It's very
I
fast.
could have a water balloon launcher.
Yeah.
It has a rocket engine on the back.
Okay, one more example. One more example. This one will get you prepped for one that's similar in your homework assignment. forces with magnitudes of 2,000 newtons and 900 newtons act on a machine part at angles of 30 and negative 45 degrees respectively. So I'm thinking about, I have two different issues happening, right? So I'm going to think about like two different vectors. I'm going to think about a u and a v. So I'm going to say that the magnitude of u is 2,000 and the magnitude of v is 900. And then they act on the machine at angles of 30 for u and 45 for v, or sorry, negative 45 for v.
What's that be 315?
Yes. Since it's, so like if you draw yourself a picture and you think about the 2,000 newtons and 900 newtons acting on the machine part, we'll put the machine part at the origin, angles of 30 degrees and then negative 45. You can use in this one negative 45 or 315. Like they have this, they're coterminal, so they have the same cosine and sine. So you can change it if you want to be positive 350. More importantly is if you have something in the second quadrant, because then your cosine and sine would have different signs, positive and negative. Okay, but I'll use the negative 45 on this one. And then like I've got 2,000 newtons and I've got 900 newtons here. Okay. That's just all like setup, right? So I'm just like basically rewriting the stuff that's all in words. Okay. And so now I'm going to read that very last sentence. Find the direction and the magnitude of the resultant of these forces. So what things are you going to need?
Components form.
You're going to need component form for U and V so that you can do what with them? Resultant. Add them. So first you're going to get component form for U and V so that then you can add U and V together, and after you add U and V together you'll have the resultant. Then you still have to do direction and magnitude. Okay. So I would do component form U equals 2,000 times cosine 30 and 2,000 times sine 30. And then I would do V is 900 times cosine 30, oh sorry, negative 45. And 900 times sine of negative 45. And that's going to be what? 2,000 times square root 3 over 2, so 1,000 square root 3, and then 2,000 times 1/2, so 1,000. And over here it will be square root 2 over 2 for the cosine of negative 45, so that'll be 450 square root 2. And then this one will be sine of negative 45 will be negative because I'm in the fourth quadrant, so going down. So it'll be negative 450 square root 2. And then those are just the two individual component forms. I still have to add them together to get the resultant. Okay, so U plus V is equal to 1,000 square root 3 plus 450 square root 2, and then 1,000 minus 450 square root 2. And those horizontal and vertical components are not very nice. Do you agree with that? Okay, so this would be an example where I still have to do work. I still have to do the direction angle and the magnitude. I may just go ahead and add these together. Okay, so I might type this. Now I've done my work with the unit circle, but I may type it into my calculator and get decimal values. Okay, so my U plus V in decimals, I think I have them written down. I get something like 2,368.45 and 363.60 when I type those in. And that will be my A and B that I do direction angle and magnitude 4. So direction, theta will equal the inverse tangent of 363.60 divided by 2,368.45. And magnitude, I'll do magnitude of u plus v is equal to the square root of the sum of the squares. So you're doing a lot in one problem. If you type this into your calculator, just so that we get an answer here, you should get 8.73 degrees for the direction angle. And the magnitude should be 2,396.20 newtons is what I get. So I know you went fast, but we're close to the bell. Okay. You have a homework assignment, work on it. I will post the answer key to homework online later today. John and Callie, would you guys be my super helpers? Come up here real quick.